Good afternoon, everybody. My name is Mitchell Israel. I'll be presenting along with my partners Byul Cho, Nishtha Ram, Stein on baseball simulations using Markov principles, as well as using arena baseball simulation software.
Before going into how the simulations work, let's talk about how they're useful in today's baseball game. A few factors that teams are using them in are the lineup order, roster construction, in-game managerial decisions, and the impact of injuries on their club.
Oh, hey, didn't see you over there. It's Coach Stein of the Cougars. I'm out here filling out my lineup card, and I'm here to tell you how the processes have changed over the past year. So instead of just pondering which player I think would fit where in the lineup, I have simulation models which incorporates hundreds of thousands of different combinations, thousands of times each, and it takes into account the hitter's skills, the pitcher, the weather, and the stadium that we're in. And this has given me a better estimate of how much each lineup is going to produce on a day-to-day basis, and I think it's really helped me allocate my time better and helped our team produce more victories. Here we go, Johnny, here we go. Hey guys, another way our simulator has helped me as a manager produce more victories for this team is it allows me to plug in any possible scenario, and it goes over every decision I can make at that time and tells me the most likely chance of us getting the maximum amount of runs we can get. So this simulator has helped with in-game management significantly rather than me going based on my instincts. Howdy.
Oh, hello there. It's Adam. I'm the president of baseball operations and general manager of the Cougars Baseball Club, and I wanted to explain how this simulator helps me in my transaction decisions. I can plug in any possible transaction and how it affects our team or other teams, and it shows me thousands of simulated seasons in which I can project standings and show what % chance we have of making the playoffs and even with our chance of winning the World Series. This simulator has really given me a strong basis of whether I am making positive expected values for our decision team. I don't know why my accent sounds like this today.
So what is Markov chain? It is a stochastic process in which the probability of particular state of the system in the next interval depends on the current state instead of defined transition probabilities. And to simply put, we don't get any additional information about the future by gathering information about the past. Hence, in the example here, past is crossed out, which indicates the Markov property.
A 1997 study in Operations Research Journal uses the Markov chain method not only to evaluate individual players, but also the team's performance as a whole. This paper studies the influence of batting order on team performance, estimates the number of games a team can expect to win in a season, and calculates the distribution of the runs scored in each inning.
As indicated in prior slides, Markov chain model of baseball has frequently been used in literature for more than 40 years due to common understanding and amount of detailed data that is readily available. In the baseball example, it is utilized to model the progression of baseball. One team bats until 3 outs have been made. Markov chain corresponds to the position of the runners on base and numbers of outs. There are 8 possible runner locations, which is derived by 3 bases, each of which can be occupied or not. So 2 to the 3rd equals 8. And 3 possible number of outs, 0 out, 1, or 2. So total number of state is 8 times 3 equals 24. So in this example, you can see that there's 1, 2, 2, meaning runners on first and second base, and number of outs is 2. Now that we have better understanding of Markov chain in baseball, let's now discuss the state transition probabilities. State transition probabilities, noted Pij, models the chance of current state batters' plate appearance will change the state of system from I to J. I is current state and J is the next state. For example, suppose state I, 1, 0, meaning runners on first and has 0 out, and state J, 0, 0, meaning no runners on base and 0 out. The only way to get from state I to state J in a single transition are for the batter to hit a home run, if not some error. So the next state is 0, 0, since it still has 0 out and no longer are the runners on base since the runners scored. So in this image, it starts with runner on third base and 1 out. So the example shows basic baseball events such as pass ball, outfield assisted double play, home run, and etc. So for visualization purpose, here are two potential transitions. First is potential transition of no runner with 0 out turning into runner on first with 0 out since the pitcher hit the batter. Second is potential transition of runner on first and 0 out turning into runner on second and 0 out, or no runner and 0 out, 1 out.
The study sets up each player with a 25 by 25 transition matrix. At any point in a half inning, a baseball game can be in one of 25 states. 24 of these states correspond to 0, 1, 2, or 3 runners on the bases, of which there are 8 possibilities, and 0, 1, or 2 outs. The 25th state corresponds to the end of the inning when the third out occurs. The method is only limited by the available data and can use any reasonable deterministic model for runner advancement when sufficiently detailed data are not available. The approach may also be adapted to include the effects of pitching and defensive ability. The results of the study showed that optimal batting orders can expect to win approximately 4 more games per 162 game season than the worst order. The team slugger, that is to say the player with the highest slugging percentage, should not bat fourth, and the pitcher should not bat last. There are limitations to what the model can include. For example, information on how a batter performs based on the particular runners on base or the current score of the game.
Stratomatic is a game that debuted in 1961 that uses cards and dice to simulate a real baseball game. It was amongst the first baseball simulating methods and is still used today. To play, each mock baseball player has a 2-sided card, and there are 3 6-sided dice. 2 of them are colored, and 1 of them is white. There's also a 20-sided die. For each batter and pitcher matchup, you roll all 3 6-sided die. The white die refers to whether you use the batter's card if you get a 1, 2, or a 3, or the pitcher's card if you get a 4, 5, or 6. And the 2 colored die refers to the player's card, which states the outcome of the at-bat. The 20-sided dice comes into play if the card says so, in order to be more specific on outcome probabilities. Data has proved that Stratomatic reflects an 85% approximation of the real effects occurring in professional baseball. Not bad for a game that just uses cards and dice. Some of the limitations are that dies 1 through 6 and 1 through 20 are good enough for this game, but in order to be as specific as baseball data is, they would need to be refined significantly.
Compared with the previous example, this is a modern simulation from the dice game that is just shown in the Stratomatic. Here we show how arena simulation can be worked with to predict batter outcomes on a batter-by-batter basis. Based on previous year statistics and career averages, the simulation model produces an outcome of each at-bat. By comparison to the previous Stratomatic, the accuracy of the player's statistics are not limited to significant digits on cards or paper and can be more accurate to gameplay as they use the computer simulation model. Next, we show the underlying simulation for the arena simulation problem. The top shows the underlying simulation for a hit if produced or if it produces an out. If the hit is produced, you are brought to another randomization to determine the number of bases that are awarded. The table below shows the metrics for analysis found in the article Using Analytics to Challenge Conventional Baseball Wisdom by Reeves, Rakes, and Dean out of Virginia Tech University. 4 tests were run, 3 testing 3 levels and 1 testing the 4th, and 1 testing 4. The outcomes of types of hitters that are put within a lineup and the lineup order are particular interest in comparison with the previous study. As shown in the chart, players with better slugging percentages can often be as productive as teams that are the best sluggers, or their power hitters. Teams that compose of hitters that bat above their batting average by 60 points with men in scoring position are attributed with producing 1 additional run per game that increases the total of wins per season by as high as 5.5 games with an average of 4 runs per game. Teams that hit below their team average with runners in scoring position hit below at 68 points cost their team 1 run per game. In conversely, with the Markov chain approach to baseball, the results found that the effect of a team's batting order was approximately 0.01 run per game, and 2 games over the course of a season. However, the arena simulation had the effect of a randomized batting order increase the number of runs per game by 0.15 runs higher than the traditional descending or the traditional batting order of having your number 4 or highest slugging percentage hit 4th in the order. This is what most of what the previous article suggested. Additionally, we attempted to run our own simulation using a Python code. We attempted to run a single season historical data into a simulation of one team against another using a 10,000 simulated games over the course of those 2 teams playing a 9-inning baseball game. However, due to this initial test, we ran into problems with a program for running statistics and base running constraints. Similarly to the Markov model, we then proceeded to adjust and remove base running from the model and change the assumptions to include a recency bias and a weighted average for the past 3 years from 2019 to 2017. For 2019, we used a weighted model of 1/2. For 2018, we used 0.375, and for 2017, we used 0.125. Unfortunately, due to the existing COVID-19 crisis, as well as the time constraints of the semester, we were unable to complete this simulator. However, we do believe, given the additional time that would be necessary, and without these limitations, we would be able to complete the simulation and produce this output of a game-by-game simulator.